So we're going to spend a little bit of time talking about building a predictive model. Now a reminder, our focus in the course is much more on building models to estimate the effect of some variable on an outcome. So this is a little bit of a side topic. There's not going to be any, or not much formal assessment on this. There is, on one of the assignments, an option where you can work on building a predictive model if this is a topic you want to explore a bit more. So there's some room for you to dig into that if you want in a very low stakes way. So what I want to do is give some guide or some suggestions, some things that are important to consider and think about when building a predictive model. So the first thing I want to say here is that really the goal here is you want to maximize the predictive power of the model. Okay. But one important thing, you want to make sure, so but you want it to make good predictions on future data or on new data. Okay, so there's this idea, and I'll bring it up a few times as I talk about this, but there's this idea of overfitting, where you're fitting your model too much to the specific set of data you have, and it's not going to make good predictions on new sets of data. Okay, so there's this fine balance between trying to get your data, trying to get your model to make good predictions, but you don't want it to be making good predictions just for the set of data it's being trained on. You want it to make good predictions on other sets of data it hasn't seen yet. So we want a balance of trying to maximize the predictive power of the model without overfitting the model or making it too specific to our observed data set. One thing we've seen through the course is that including all X variables is a bad idea. And we've seen a little bit about why that is. We looked at a real set of data as well as some simulations to see what happens when we just throw everything we have at the model. So doing this can lead to bias, can lead to bad predictions, and it can definitely lead to what we just talked about, the idea of overfitting. Right? So if some variable, some X variable is not really related to the outcome in reality, but in our data set has some weak association, that's going to inform the prediction. Where when we use new sets of data to try and make prediction, it's going to give bad predictions because that variable is actually not related to the outcome. Right? If you remember, if in reality, some variable, let's just call it x5, some variable x5 and the outcome have absolutely zero correlation, when we get a sample of data, the correlation between those two is not going to be zero. Right? It's going to be something probably pretty small, but something that's non-zero. There's going to be some weak association that shows up by chance. Okay? And including all of the X variables, you can take all these weak by chance associations and put them into the model, when in reality there is no association between those variables and the outcome. Okay, so that's why including all the X variables is a bad idea. So on that note, we need to validate the model. We need to look at prediction error. I should say on new data. And we'll talk a little bit about the idea of validation. Mostly what we're going to do is say some of the topics and ideas in name, give the one-sentence introduction to them, and refer you to read more about them if you want to explore this a little bit more on your own. But as I was saying, the idea is we want this model to make good predictions for data it hasn't seen yet. And so that falls under the umbrella term of validating the model. And there's lots of ways to do this. We'll mention some of them. But really, what we want is to see how well our model can predict, or what the prediction error is for new data, right? The problem with things like R squared that we see from linear regression models is R squared in the linear regression model looks at how well can our model predict the data that was used to train the model, right? So again, that set of data we use to build the model to decide what should all the coefficients be for the model. And then R squared looks at, well, how well can that model predict that data? But that data was used to build the model. Right? So it's not to say that R squared is bad, but it's not the best measure of how well can our model actually predict new sets of data. Right? R squared from a model is always going to be higher than the actual real R squared. If we give it a new set of data, it's never going to predict as well as it can predict the data that trained it. So we'll talk a little bit about some different approaches to validating the model. Again, mainly in concept and the kind of quick intro version. Reminder, if x2 and x3, so just two variables, are collinear, include just one. So check for collinearity, and in predictive models, especially the idea of multi-collinearity comes in. Right? So if variables x2, x3, x4, and x5 contain all the info that x7 does, we don't need to include x7. Right? So there's this idea of checking that and trying to remove redundancies. I won't write it down, but I'm going to say a reminder, in predictive models, there is no concept of confounding. Right? If our goal is just to input variables to the model, get a prediction, there's no interpreting coefficients from the model, so it doesn't really make sense to say that the effect of two variables are mixed together. If our goal is not to interpret the effect of individual variables, we don't need to worry about this idea of confounding. It doesn't exist. A reminder, and this is sort of related to the don't include all x variables, but including more x variables will always increase the R squared. Right? So if we have some other variable that in reality is not related to the outcome, if we put it into our model, it's going to bump up the R squared by a little bit, always. Okay? By chance, it's going to go up a little bit. There's the idea of adjusted R squared, which we've talked about earlier in the course. That tries to counterbalance the effect of adding unnecessary variables to the model, but it doesn't always work so well in counterbalancing, and really, we want to take control of this ourselves. If we know that a variable is not related to the outcome, if it doesn't make sense conceptually, if statistically it doesn't really seem to be a good predictor, let's exclude it from the model and not leave things like adjusted R squared to try and take care of our problems. Let's take care of them ourselves. So including more x variables will always increase the R squared that's in the model, but it will lead to overfitting if that x is not important. Okay. What I mean by not important is if it's not related to the outcome or its association is so weak, what it's going to do is just introduce bias. The model is going to be overfit. Right? It's going to be using that variable to make predictions and increase its predictive power. But if that variable is actually not important, when we get a new set of data, it's still going to use the info from that x variable to make a prediction when it shouldn't really be using that. Right? It's not an important variable. And one kind of final note I want to say before I get to talking about approaches or ideas for validation is you want variables to be, so the few things that are important with the variables in predictive models, one of the most important one is available at the time of prediction. So let me try and think of an example here of what I mean by that. Suppose you're in the ER, the emergency room, and you have patients come in for a certain reason, and you need to try and decide, should we send them down path A or path B? Right? So you might be trying to decide, do we think that some adverse event is going to happen, yes or no? Right? And you might have some quick checklist or something you look through that tries to decide, yes, something adverse is going to happen. Let's send them down path A so we can deal with it quickly. No, we think something's not going to happen quickly. Send them down path B where we can take a bit more time with them. And suppose that one of the good predictors is measuring some level of something in their blood. And that might be a really good prediction of whether or not this adverse event is going to happen. But if you have to draw blood, send it to a lab, wait a day or two or maybe a week for the results to come back, even if that's a great predictor of the outcome, it's not going to be useful for your goal of the model, right? If your goal is to, someone shows up in the ER, quickly go through this checklist of items and decide, do we send them path A or path B? So it should be available at the time you're making the prediction. It should be reliably measured. So again, you don't want it to be that if a different person evaluates this individual, they're going to come up with a different value or different score or different number for this variable. Right? You want it to be as objectively measured as possible, so it's not relying on that evaluator. And then I guess, I don't know if I should add this in or not, but I had in my notes saying that cheap. I guess it depends on your budget and your goal and so on, but, so maybe I'll leave that out. So what I'm going to do shortly is get into talking a little bit about some ideas of how we can validate the model. Right? So how we can look at prediction error on new sets of data. And the list I'm going to give you is not going to be complete and exhaustive. It's going to give you some ideas and give you a feel for how we can try and validate a model. And it's going to give you the introduction to that and allow you to explore the concept of validation more if you want to.
Stick around, guys. There's more to see, and please stay safe.